Okay, now to test the capacitors with the multimeter, what you have to do is look for the letter F or MF on your multimeter, which would mean farad. Now, in order to test the capacitors, the most normal thing to do first is to carefully discharge those capacitors. Since some capacitors may be fully charged, please be very careful, especially with high-voltage capacitors. For example, here I have a capacitor. It's a 33 microfarad capacitor, which has a low capacitance but high voltage. In this case, I suggest you short-circuit its terminals using a screwdriver, but without touching the metal parts of the screwdriver. Once you short-circuit it, it's very likely that several sparks will be generated, so you must protect your eyes. Always do it taking care of your eyesight, moving the condenser a little further away. The sparks generated will depend a lot on the capacitance and voltage of the capacitor. More voltage and more capacitance mean more sparks. Therefore, our capacitor must always be discharged. But in the case of low-voltage capacitors, it's not a problem if you touch them. However, they must also be short-circuited, just like non-polarized capacitors. They short-circuit them, and only then can they use the multimeter in capacitance mode. Now, this one here has the code 225, which is the code used for non-polarized capacitors. The J is the tolerance, and there we have the working voltage. That means this one would be 2.2 microfarads. Do the calculation and you'll see that would be the value. So let's measure it with the multimeter. It says there that it's 2.15 microfarads, which is quite close to the theoretical value. Remember that capacitors have tolerances of 5 and 10%. In the case of the J, it would be 5%. In the case of polarized capacitors, there's no need to place the positive lead of the multimeter on the positive terminal of the capacitor if the capacitor's voltage is greater than 5 volts. So there shouldn't be any problem if you do it the other way around. Notice that I'm going to connect the positive lead to the negative terminal, and the negative lead to the positive terminal. And we have 2,200 microfarads, which is equivalent to 2.2 millifarads. And looking at the capacitor's specifications, we see that it is indeed 2.2 millifarads or 2,200 microfarads. This capacitor is in good condition. Let's look at a capacitor in bad condition, one that blew the last time I used it. The capacitor was damaged because I didn't check its operating voltage. This is the capacitor that bulged because I installed it on a circuit board where the voltage was much higher. Let's check its condition by measuring its capacity. It says it's a 1,000 microfarad capacitor. Remember to short-circuit the terminals first, and only then can we measure it. It's okay if you touch one of the terminals. And we have 660 microfarads. Keep in mind that this is in farads, that's why it has a 0 in front. But you should only consider the 3 digits, which would be 650 microfarads. It's lacking quite a bit. It's barely at half its capacity. Therefore, we can say that it is no longer useful. Now let's see how these polarized capacitors, or rather electrolytic capacitors, are constructed. They are typically made up of 2 metal sheets wrapped in an insulator or cardboard. There we can see the metal sheets used to store energy. The longer the sheet, the greater the capacitor's capacity. And finally, we can see the electrodes or pins. One of them is connected to one of the sheets, and the other is connected to the other metal sheet. Remember, the longer the sheet, the greater the capacitor's capacitance. And there we have the electrodes. The cardboard would be our insulator. The metal sheets, our insulator or dielectric. And that's how capacitors are constructed.